Welcome to anyone who's just joined us or who's joining a bit late in the session. Don't panic. We just started at 6. We're doing some multiple choice questions. We are going to be running up until 8 p.m. So don't panic if you think you are late. Okay, all we're doing right now is we're doing this multiple choice question number 1. Tell me what you guys feel like the correct answer is. A, B, C, D. Which one best illustrates balanced forces? Okay, we got some nice answers there. Thanks to Nice Boys, Sino, Mangwane, Kensani, Remo, Bientles got answers there. Thank you guys there on TikTok. Thanks to Brilliant. Thanks, Masejo. Thanks, Katlejo. Thank you guys for all your answers there. Okay, I'm going to give those who haven't answered, you're going to have 15 seconds. Quickly post your answers. Remember, the golden rule is, guys, never leave multiple choice blank. Never leave it blank, right? If you leave it blank, 100% chance of getting it wrong. If you guess, you have a 25% chance of getting it right. But if you join our lessons every day, you're going to increase those chances of getting it right and making sure you can nail those marks. So let's make sure we can go in there. All right. 5 seconds to go. If you haven't answered, just drop your guess now in the chat. 5, 4, 3, 2, and 1. Thank you guys so much for your answers. I see lots and lots of answers. So let's go through them all quickly, right? So when we're looking at this there, we can see A, it says a person lifting a heavy object from the ground, right? So again, that is not going to be balanced forces, because when you're lifting an object from the ground, the object was initially at rest on the ground, you have to then initially accelerate it up, right, for it to start moving off the ground. So from the ground to it starting to move, that's got to have a net force to make it move up to initially start the object moving. Not going to be balanced forces. Okay. If you got A, don't feel bad as long as you understand where the mistake you made was. Okay, let's look at B, a big rock free falling to the ground. And again, B is not going to be the answer, right? Why? Because free fall is an object that's under the effects of gravity and gravity only. The free body diagram is going to have what? It's going to literally just look like this. It'll be a reasonably sized dot and then FG coming down like that. That's not those are not balanced forces, because to begin with, it's only one force. So we know that B is not going to be it. Then let's look at C, a light stationary object, right? A light stationary object. The first thing that tells me about balanced forces there is going to be this word here, right? Because usually if you think back to Newton's first law, right, an object will remain in a state of rest or constant velocity unless a net or unbalanced force acts on that object. So when an object is stationary, you know you've got no net force. That's going to be balanced forces there. So C is going to be our correct answer. Let's look at D again and look at why D might not be the correct answer. Because D says a force of a box on the earth and a force of earth on the box. So now remember, for forces to be balanced, the forces must be acting on the same object. For D, you've got a force of the box on the earth and the earth on the box. Those two forces are exerted on different objects. One force is on the person, one force is on the earth. So yes, those are examples of Newton's third law, which is going to be an action and a reaction force, but not balanced forces. Balanced forces, you must think of Newton 1. The forces must act on the same object. So then we know there that D cannot be the right answer. And for those that are joining us for the first time, it's important that when you do multiple choice questions, that's why I do it this way all the time. It might take more time, but it's important because it shows us the process we must follow. Don't just go and say C is correct because I know it's correct. Tell yourself and show yourself why are the other ones not correct. That's very, very important. Okay, if you guys got it correct, give yourselves a round of applause. If you didn't, don't stress. You've got a number of questions coming up that you can redeem yourselves, right? Okay, let's have a look at the next question. So there's the next question there. The next question then says, an 8 kg box is placed on a rough surface as shown below. If a force of 16.5 newtons is applied to the box, it accelerates 1.5 meters per second squared to the right. Let me just quickly make sure we can see it. There we go. The frictional force between the 8 kg block and the surface is 0, 4.5, 10.3, 29.4. What is the frictional force? Right? Quickly give there the answer. A, B, C, or D. If you need to do any calculations, you can do your calculations on the side. I'll give you guys a bit of time just to be able to look at that. For those that have just joined, I'll quickly repeat the question. It says an 8 kg box is placed on a rough surface as shown below. The frictional force is 16.5. A force of 16.5 newtons is applied to the box. It accelerates at 1.5 meters per second squared to the right. The frictional force between the 8 kg box and the surface is A, 0, B, 4.5, or C, 10.3 newtons, or D, 29.4. Okay, have a quick look and then tell us which one you guys think it will be. As soon as you're done and you have your answer, you're more than welcome to post it in the chat. Thanks for the quick fingers there from Junior and Bentle. Lotlhogonolo's also got some quick fingers there. Thanks, guys. Divuen is there also with the quick fingers. And Natasha, thank you guys for your quick fingers. Those that haven't answered it yet, don't worry, you still have time. Don't panic. I'll give you another minute 30 or so to answer this particular question. Guys, please remember, when you engage and when you take part, it's really when you start to learn as much as possible. So make sure you do post your answers in there. Multiple choice is easy. The worst thing you can do is just guess. And what happens, even if you get it wrong, you're going to leave here with the right answer. So don't panic too much about that. Cool. Right. 30 seconds for those that haven't given their answers yet. Okay, while you guys are busy, please, just a reminder to those, if you've given us your answer, you're watching for the first time, or you've watched a number of times, but you haven't followed us, please just click that button. It really helps us quite a bit with our content. Thank you so much. Okay, 10 seconds to go. Quickly get your answers if you haven't got them in. If you're still wondering and you're still stuck, just give your best guess. 5, 4, 3, 2, and 1. All right. Let's have a look at which ones could be the right ones, right? So for this question, I'm going to show you, first step, I'm going to try and eliminate a few of them first, and then we can try and pin down, right? So the first thing we know here, right, is we're dealing with, they told us here, it's a rough surface, right? Knowing that we're dealing with a rough surface, the first thing I know that our frictional force cannot be A. Already I can take that away because a rough surface means I must have a frictional force, okay? Another one I can very easily remove from this particular case is going to be D, right? Because if my frictional force, remember, frictional force always acts opposing my motion. So it's going to act in towards the left, right? Now, if my frictional force was D, 29.4, I would really end up with, I wouldn't have enough acceleration to take me to the right-hand side because my friction would be greater than my force pushing me that way. So I know immediately that it can't be D because my frictional force has got to be less than the force being applied. So I know it can't be D. Now I'm left with either B or C. And the way to figure out B or C is to do a quick calculation, right? And then once you've done your quick calculation, you'll be able to figure out what you're going to be dealing with. And in this case, we're going to be applying Newton's second law, right? Newton's second law states the following: that when a net force is applied to an object, that object will accelerate in the direction of that net force. The acceleration will be directly proportional to the force applied and inversely proportional to the mass of the object. So we can then plug that there and say, well, okay, cool. F net's going to be equal to MA. What's our F net? F net's going to be whatever force is pushing me forward minus the forces pushing me back. So it's going to be F minus my friction is equal to M times A. And then you can plug your values in, right? You know your force is going to be 16,5. Let's assume right is positive and left is negative. Minus the force of friction, that's what I'm trying to solve there, is equal to my mass, which is 8 kilograms, times acceleration given to me as not 1.8, but rather 1.5. And then if you put that into your calculator and you solve for F, you'll see you get an answer for F, the force of friction of 4,5 newtons, which in that case, we've now ruled out C, and we've figured out that B is going to be the correct answer. If you got the correct answer, guys, please give yourselves a round of applause. If you haven't, don't stress, there's more questions to come. I see there's a question already on TikTok there. Someone there's asking, What grade is this, right? This is dealing with a grade 12 physical science paper. You can see there in the live info as you start, right? We're about to get started and we're going to get going soon in terms of the long questions. For now, we're still doing our multiple choice questions. Awesome. Let's look at our next question, guys, for you guys there. So the next question is going to be as follows. 1.3 says, a ball is dropped from a certain height above the ground and bounces a few times as it hits the ground, right? The velocity time graph below describes the motion of the ball from the time it is dropped. Ignore the effects of friction. I'm going to zoom out a little bit so you guys can see our options. So we've got a velocity time graph there, and then the questions are below in terms of which one to pick, right? In relation to the velocity time graph for the bouncing ball shown above, which statement below is correct? A, down is taken as positive as the positive direction, and the ball is at its highest position of its bounce at point C. That's the first option. B, down is taken as the positive direction, and the ball is at its highest position of its bounce at D. Or C, down is taken as the negative direction, and the ball is at its highest position of its bounce at C. Or D, down is taken as the negative direction and the ball is at the highest position of its bounce at D. Which one do you think is going to be the one there, A, B, C, or D? I'll give you guys 30 seconds to quickly think about it, have a look at it, and give us the correct answer. Go for it. If you just joined us, we're doing a multiple choice question. All I want you to do is read through it quickly. Give me your answer, A, B, C, D. I'm going to give you guys 30 seconds to another minute, and then we'll be able to do the question together. Bianca asked to see the statement up at the top. I can quickly try and do this. And then it says there, a ball is dropped from a certain height above the ground and bounces a few times as it hits the ground. The velocity time graph below describes the motion of the ball from the time it's dropped. Ignore all the effects of air friction. Okay, thank you for the quick fingers and everyone that's been throwing their answers in there. 20 seconds left, and I'll give you guys some more time to answer. Okay, guys, quickly, if you haven't got your answers in, put your answers in. You've got 10 seconds to go. If you're stuck and you're unsure, just give your best guess. Try in your head to eliminate one or two options and then go straight for it. 5, 4, 3, 2, and 1. Thank you guys so much for your answers. Let's have a look at which one is going to be the correct answer, right? So first of all, let's look at it. The ball is dropped from a certain height. So let's track the motion. I'm going to zoom in on this, and then we'll try and figure this one out. So the ball is dropped. What does it mean when a ball is dropped? It means it's got initial velocity is 0. There's a very fun video on our YouTube channel that I want you guys to watch. It's the video that's highlighted. When you get to our page, it's the video that just says it's called gravity. And we really go into some fun scenarios of vertical projectile motion at Bounce. Bounce is this awesome trampoline park. Go watch the video. So you learn about the various terms where when an object is dropped, it means the object has an initial velocity of 0. So this is where we start with our entire motion, right? Once we start there with our motion, when you drop a ball, what happens? The ball goes in the downward direction. Notice now here, if the ball goes in the downward direction, that is going to be the negative part, because the top part is the positive side of my graph. It's the negative part of my graph. So when I go down, in this case, we can see that down is going to be negative. Very, very important as the first step. It increases its velocity, right up until the point where something happens. So we can see it goes down, 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 down. Then there's something that really happens in this point here between A and C, right? And not the political party. So between A and point C, that is when the ball hits the ground. So it's going to increase its velocity in the negative direction. So it's speeding up downwards until it hits A. A to C is when I'm on the ground, right? Very, very important. I'm on the ground between A and C. And then from C, I'm now, you can see I've got a very high positive velocity at C, but I'm still on the ground. Now my very high positive velocity at C, I'm now going to start moving in the upward direction, but my velocity is decreasing with time, right? I'm slowing down, I'm accelerating because I'm going up to my highest point. Because what happens at your highest point? Your velocity equals 0. So we can clearly see there at D is the highest point with our 0 velocity. Then from D, I start going again, negative direction, which we defined as down clearly from the first start. I'm going to now start increasing my velocity in the negative direction until I reach this point here, which is going to be again hitting the ground. From the ground, my velocity is going to change from fast negative to fast positive, still on the ground. After that point there, I start now with a very high velocity moving upwards, right? Slowing down until I reach another maximum height at this point here. And then I move down now into the negative direction, increasing my speed until I hit the ground for the final time. So let's quickly have a look at that again as a recap. Start off at 0 in the air. I get dropped. The ball goes down, increasing my velocity until I hit the ground. Remember, I'm increasing in the negative direction. From A all the way to C, I'm still on the ground. I'm just changing direction. Initially, I was moving down. On the ground, I'm changing direction. At C, I'm moving up, but I'm still on the ground. After I leave C, I've now left the ground. Now I'm going up, but I'm slowing down. My velocity is slowing until I hit 0 at D. What happens at 0? That is maximum height. Maximum height, I turn around and I'm start moving in the negative direction. Negative direction, I go down until I hit the ground again. At this point, this dashed line, I'm still on the ground, but now I've changed. I'm moving back up again. It's the second bounce. I move up, my speed slows down because as I go up, my speed slows down. I'm converting kinetic energy to potential energy. I hit my maximum height again, and then I start moving down, hit the ground for the final time. That's my motion. I hope that makes sense. So then if you can see that, you can then clearly see that our correct answer there is going to be D, where we said down is taken as positive because what happened is that ball was dropped, right? Sorry, down is taken as negative. Ball was dropped, which means I started moving in my negative direction when I was dropped towards A. So that's the first part that we can see there. And the ball's at its highest position of its bounce at D. And that's correct. Why? Because at D, my velocity is 0, and that's my maximum height. I hope that makes sense to you guys there. I'm not going to go through A, B, C, because I've shown you guys why D is correct in this case there. Because then we can clearly see down is taken as the positive direction. That's incorrect. So we know A is not it. B, down is taken as the positive direction. That's incorrect. So we know it's not B. C says down is taken as the negative direction. That is correct. The ball is at its highest position of bounce at C. That's not correct. C is the ground. Highest position of the bounce is D. So we know that C isn't correct. Therefore, D is the correct answer. If you got the correct answer, give yourselves a round of applause. If not, don't worry. Two things are going to happen. Number one, you now know how to do it. Number two, we're going to then move to another question where you can then still redeem yourselves. Okay, awesome. Let's go to question 1.4. So question 1.4 looks as follows. It says, two identical solid spheres, each with a mass m, and traveling at a speed v, move towards each other in an isolated system. The spheres have a head-on elastic collision. Very important. You see that it's highlighted there. Which statement is correct for the collision as described above? A, the spheres stick together on impact. B, the total kinetic energy after impact is mv squared. C, the total kinetic energy before impact is 0. Or D, the total momentum before impact is 2mv. I'm going to give you guys 2 minutes to try this one quickly. Once you know the right answer or the answer you think is correct, please post that in the chat as soon as you have it there. Cool. Anyone who's just joined us, we're doing this multiple choice question. Quickly have a look at it, put the correct answer in the chat, and then we're going to go through the question together. And if you're watching us right now for the first time, or you've been watching us and you haven't followed us, please click that follow button. We would really appreciate it. Cool, guys. If you haven't put your answers in yet, just double check again. You've got about a minute to go to put your right answers in there. Neso G just asked, what grade is this? This is going to be grade 12 Physical Science Paper 1 revision. You can see in the live info as you join, it'll tell you there. Cool, guys, quickly get your answers in before we go and look at the answer, the final answer together. Okay, 10 seconds to go. Five, 4, 3, 2, 1. Fantastic. Okay, let's have a look at this thing together, right? Quickly going through the question to remind ourselves of what the information all means. So two identical solid spheres, each with a mass of m, traveling at a speed of v. Very important that they said speed of v, not velocity of v, right? So same speed, different velocities because it's in opposite directions. Move towards each other in an isolated system. Isolated system means we're not going to gain or lose energy in this particular system. The spheres have a head-on elastic collision, right? What does elastic collision mean? It means our kinetic energy or the energy through the collision is going to be conserved. Energy before will be equal to energy after. Very, very important. Okay. Now, with that in mind, we have to look at the following statements. Which statement is correct for the collision as described above, right? A, the spheres stick together on impact. Now, if they're moving at the same velocity and have the same mass, if they stick together, it means they're going to come opposite directions, collide, and then once they've collided, they're going to just be stuck here together with no velocity, right? We know that that can't be the case because we were told that it's an elastic collision, right? Because that would mean that afterwards we would end up with a kinetic energy or an energy value in my system of 0. And it can't be the case. The energy must be the energy that we started off with before. So we know that A is not the correct answer. B, the total kinetic energy after impact is mv squared. Well, let's have a look. What was the total energy before impact? So let's quickly calculate that. So energy before, the total energy is going to be the energy of the first one. Let's call it energy of A plus the energy of, let's call it B. What is kinetic energy? Half mv squared plus another half mv squared. What is half mv squared plus half mv squared? It will give us 1 mv squared, or simply mv squared. And if that's the energy before the collision, right? Remember that energy is a scalar, so the direction doesn't matter. The energy together is all that matters. So mv squared is my energy before. B says the total kinetic energy after impact is mv squared, which is the same as my energy before. And because they said this is an elastic, quickly highlight this, an elastic collision, we know that energy before must equal energy after. That's how I know that B is going to be my correct answer. Hope that makes sense to you guys there, that B is going to be the correct answer. Let's look at the other ones anyway. C, the total kinetic energy before impact is 0. Not true, because we calculated it, right? Here's the energy before impact. It was equal to mv squared, so that's not true. C, the total momentum before impact is 2mv. Not true, because momentum is a vector. How do we look at that? So P before is going to be mv of A plus mv of B. So that's going to be, the mass is m. The velocity of the first one of A, let's assume right is positive, is going to be a positive v, plus the second one is going to be the same mass, m. What is the velocity of the second one, B? It's going to be a minus v, right? Minus v because it's in the opposite direction. Therefore, I'm going to have mv minus mv, which is going to be 0. Momentum before the impact was 0, not 2mv. This is not going to be the correct answer. And again, it's important, show yourselves which one is correct and why, and then which ones are incorrect and why are they incorrect. Then you know for sure that you've nailed the particular question. Hope that makes sense to everyone, guys. If you guys are still on board, still with me, please give me a thumbs up in the chat. Then I know I can continue on to the next question. For those that have just joined on TikTok, just give me a thumbs up in the chat if you're still with me. We're about to move on to the next question. Everyone who's just been there, give me a thumbs up. Thank you for the thumbs up on Zoom there. Thank you, Didi, there on TikTok and Fatso. Okay, cool. Fantastic. Let's move on. Thank you, Sino, as well. Cool. And then the next question, second last question for you guys before we do the long questions, is going to be as follows. It says, the mechanical energy of a moving object will remain constant if A, there are frictional forces present, or B, there's only gravitational force acting on it, or C, only the kinetic energy remains constant, or D, only the gravitational potential energy remains constant, right? The mechanical energy of a moving object will remain constant if A, B, C, D. Just give me a quick answer in the chat. Have a look at it. This one is a bit of an easier one. I'm only going to give you 60 seconds to answer this question. Thank you, Didi, for your fast fingers. Thanks, Edmund, as well there on Zoom for your fast fingers. Okay, everyone else still got about 45 seconds. Think it through as much as you can. I'll give you another reminder when we're like 15 seconds too. And if you haven't got the answer there, then you might have time to guess. But for now, give it a think, right? Think about what law would this apply to. That will be the biggest hint I can give you today. Okay, you have about 30 seconds to go, guys. Thank you, Reese, for your answer. Thanks, Deborah. Thanks, Prudence. Thanks, Junior. Thanks, Kansanian. Thanks, Nicole. 10 seconds to go, guys. If you haven't put your answer in or you're still unsure, worst thing you can do is, well, not the worst thing, the best thing you can do is guess, right? Quickly drop your guesses in there. 5, 4, 3, 2, and drum roll. 1. Okay, let's have a look at which one is the correct answer for this next question. It says the mechanical energy of a moving object will remain constant if, so let's think about this. That sounds very familiar. It sounds like a physics principle that we deal with, the law of conservation of mechanical energy, right? Which states that in a closed system, the mechanical energy will remain constant. So very important, in a closed system, no energy in, no energy out, only dealing with conservative forces, right? So number 1A, when there are frictional forces present, definitely not. Why? Because frictional forces take energy out of my system. They do negative work. So it can't be A, right? The next option is B, when there's only gravitational force acting on it. And that is actually correct because, again, it's in a conservative system or closed system. Gravity is a conservative force, right? So when there's only gravity acting on the object, definitely the mechanical energy of the system of the object will remain constant. Then let's say C, only the kinetic energy remains constant. And I mean, you know, in that case there, it's not always. There's certain cases where kinetic energy remains constant, but you could still have friction, right? Where I've got a force pulling an object one way, and then I've got a frictional force pulling the other way. I'm moving at a constant velocity. Yes, my kinetic energy will remain constant, but I've got energy in and I've got energy out of my system. So that's not going to then be useful. And also, I could have my potential energy increasing if I go up or down the hill. So then C will not be the correct answer. D, when only the gravitational potential energy remains constant, right? So that means I'm not changing my elevation. I'm not going up, I'm not going down, but I could be accelerating forward. I could be slowing down, which means I've got either energy in or energy out, not conservative. So then D is also not going to be the answer we are looking for. So B is your final answer. If you got B, give yourselves a round of applause. If you didn't, there's one last question for us to be able to redeem ourselves, right? Okay, let's quickly jump onto that one. Okay, the question now says, a train is moving at a constant velocity of 10 meters per second, while sounding its whistle with which has a frequency of 500 hertz. Take the speed of sound in air as 340 meters per second. What frequency will be heard by a man sitting in the train, right? Train is moving at a constant velocity of 10 meters per second while sounding its whistle, which has a frequency of 500 hertz. Take the speed of sound in air as 340 meters per second. What frequency will be heard by a man sitting in the train? Is it going to be A, 500 hertz, B, more than 500 hertz, C, less than 500 hertz, or D, no sound will be heard? I'll give you guys 30 seconds to answer this one. Okay, you guys have about 10 seconds left. If you haven't answered, please put your answers in the chat as soon as possible. 5, 4, 3, 2, and 1. Okay, time is up, guys, on this last question. And I see a lot of people pick the correct answer here, so I'm very happy for you guys. All right, so let's have a look at the two questions, the options. So when a train is moving at a constant velocity, sounding its whistle, it's got a frequency of 500 hertz. Okay, this is dealing with the Doppler effect, right? Where we get an apparent or a perceived change in the frequency emitted by a source when there's relative motion between the source and the listener. So if the object is moving towards me or I'm moving towards the object, I will perceive a much higher frequency or a higher pitch. If the object is moving away from me, I will perceive a lower frequency or a lower pitch. If there's no relative motion between the two objects, I will perceive the true frequency. Now, in this case, what's happening, right? It says there that what's the frequency that's heard by the man sitting in the train? So if I'm sitting in the train, it means I'm moving with the train. What is my velocity relative to the train? 0. There's no relative motion between myself or that man and the train. And since there's no relative motion between the man and the train, they are going to hear the exact frequency that's emitted by the train being 500 hertz. So A is going to be our correct answer. And then why is it not B? Because there's no relative motion. B would have to be if they were moving away from each other, which they're not. C would have to be if they were moving towards each other, which they're not. D says no sound will be heard. This is going to only be true if this man was deaf or there was no air. And then there was no sound to propagate. There was no medium to propagate the sound. They didn't tell us any of that information. So we can assume that that is not going to happen. Okay, well done for everyone that got the right answer A. Give yourselves a round of applause for doing that. And fantastic, guys. You guys did really well with this section. We're going to jump into our long questions now. Please remember, it's an interactive session. Do your best to ask questions and comment when you guys are commenting. You guys have done really well in the interaction part of this session. I really enjoy teaching you guys as a result of that. Awesome. Cool. Let's quickly do that. And then we're going to jump into our first question, right? Now, again, the questions we're going to do today might be a little bit tricky, right? Don't feel too bad if you're finding them a little bit challenging, because we're dealing for prelims right here. And again, the group of people I'm dealing with here, I want you guys to be knocking out A's. So, but I'm going to take my time. I'm going to try and explain the steps as thoroughly as possible. And remember, we're going to take our time. I'm not going to rush because we've got 2 days to finish this paper. We're going to start today, and then we're going to finish off on Thursday. All right. Let's start with question 2. If we can get to question 4 by today, I'll be happy. And then we'll finish question 5 to, I think it's 10 or 11 on Thursday. So question 1, a group of learners design a device that consists of a light ball on a string hanging from the roof of a cargo truck. This device is used to determine the acceleration of the truck. When the truck is stationary or moving at a constant speed, the ball will hang straight down. So what they mean there, if the truck is not moving, what's going to happen? The ball will simply just hang straight down like that. But when it's moving, because of inertia, then the ball is going to hang at a particular angle, theta, as shown, right? But when it is undergoing a constant acceleration, A, the ball hangs down at an angle theta, as shown in the diagram below. 2.1, draw a free body diagram of all the forces acting on the ball. Now, in this particular question, I'm going to draw the free body diagram as is depicted in the image at some particular angle theta, right? So to draw my free body diagram, I have to start with my reasonably sized dot in that case there. And then we need to figure out, number 1, what are the forces that are acting on this object? While I draw my free body diagram, I want you guys to quickly post in the chat, which forces do you guys identify acting on this object? Quickly go. I'll wait for the first 2 or 3 answers. Princess says, just join. What grade is this for? This is grade 12 physical science. Abu says, and Bianca says, FG, well done. That's definitely one of the forces. So we're going to have FG. FG always acts vertically downwards, right, towards the center of the earth. Well done, guys, there. What other forces are acting there? Someone mentioned tension. Thanks, Kuto, for that. Thanks, Kamohelo, as well on TikTok. We're going to have a tension force, right? Tension force is going to be the force that is experienced as a result of that cable that's pulling my object. So we're going to have, sorry about that, a tension force acting there, acting basically at some angle theta, right? There'll be some angle theta that my tension is pulling at. I saw someone said F normal, right? Someone said F normal. Princess asking, do you do grade 11? This is a grade 11 topic. So Princess, you're more than welcome to stay for this question because it is a grade 11 topic. So you can stay for this question. So someone did say here that we're going to have F normal. So one of the reasons it's important to know how to identify your forces, right, is because in this case here, what happens for normal force? What is a normal force? Remember, a normal force is going to be a reaction force to any object that is resting on a surface, right? So if you have an object resting on a surface, that surface will exert a force back onto the object. That is what we call our normal force. So in this case, my ball is not resting on any surface. It's simply being held by the tension of that string. And that tension is essentially the reaction force of the string, right, with the ball pulling it. So in this case, no normal force, only Fg and tension are going to be acting on this particular object, right? Cool. If you got that right on your side, well done. Give yourselves a round of applause. Let's move on to the next question. Princess is asking, do you do YouTube videos? Definitely so, right? We do YouTube videos. Go to our YouTube channel, youtube.com/the learning spaces. You'll find lots of stuff there. There's another question here from Nicole. Nicole's asking, is there any other way we could have drawn F tension, or is it only at that angle that you've drawn it? The only other way, Nicole, to have drawn this is if you had done it in components, right? So if I had done now this one, that's going to be drawn in red, FG, and then you're basically going to then draw, let me quickly put this straight there. That was going to then be you can call it TY, right? The Y component of tension. And then this one here, which you can then call Tx, the X components of my tension. That's the other way that you can draw this particular free body diagram. I normally prefer to draw the forces exactly as they are, especially when I was asked to draw a free body diagram. Then I will do components for my own calculations. But you are more than welcome. Lately, they do accept components in the exam as they do it. Awesome. Thank you guys so much. Let's quickly, and then Princess says, you just gained a follower. Thank you so much, Princess. We really appreciate that, right? Okay, so let's look at 2.2. And it says, in this case, the mass of the ball is 50 grams and the angle is going to be 18 degrees, right? With that, then they're going to ask the following question. calculate the horizontal force on the ball. So we need to look at what horizontal force is going to exist on the ball. So basically, we need to calculate that Tx, that x component of my tension, right? So in calculating that x component of my tension, I need to basically look at, well, number one, what is the tension? Once I've got the tension, I can then work out what is the x component of the tension going to be, right? Cool, let's quickly have a look at that. So to do that, I'm going to use my FG to calculate my tension in the y direction, and then I'm going to then use trig to basically sort out what is the x component of my tension. So first of all, we need to calculate FG. So in this case here, we know that Fg equals mg. That is going to be 0,05 grams. Remember, it's got to be in kilograms. It was given to us in grams. We need kilograms times the gravitational acceleration, which is going to be 9,8. That will then give me a final value of 0,49 newtons. That is the value of my Fg, right? Now, I need to also then go and find what? I need to go find I can find my Ty, my y component of the tension, because that is going to be equivalent to my Fg, because in the vertical direction, I am at equilibrium. So if you look at this here, right, this object is going to be moving towards the right. So left and right, I've got an acceleration. But up and down, I don't have an acceleration. So my forces up and down have to be balanced. So then I know that any force up must equal any force down. Ty is going to be equal to Fg. So then I can easily say here, Ty is equal to Fg. If you want to write it out in any longer format, I can literally simply just say, by Newton's first law, my F net is equal to 0 because m times 0. And my F net's going to be, let's say, forces up minus forces down. So I'm looking at my Ty minus my Fg is equal to 0. And then if I take Fg on the other side, I can clearly see Ty is equal to Fg. And we know that that's going to be equal to 0,49 newtons. We just worked that out, right? Okay, now with that, I need to go and find my Ty. So the best way for me to do this is I'm going to draw what we call a vector diagram. Vector diagram or vector triangle helps me work that out. So in my vector triangle, I basically have tension as a force this way, right? That's my tension. Tension is going to be broken down into my X and my Y, right? So then my Y is going to go up this way. That's Ty. That's my full tension. And then finally, somewhere this direction here, I'm going to have my Tx. And this will be my angle theta down here. So I have now got the following value. I've got Ty. I need to find Tx. So I've got, there's my hypotenuse here. I've got adjacent. I've got opposite. I've got theta. I need to find that. So we can very easily say tan of theta, right? Right, equals what? Opposite over adjacent, right? So it's going to be Tx over Ty. So to solve for my Tx, that's my horizontal force, I know that Tx is simply going to be, Ty times tan of theta. Let's plug our values in. Ty we solved to be 0,49 newtons. Tan of theta is simply going to be tan. We were told it's 18 degrees. Tan of 18 degrees, sorry, 18, not 180. Plug that into your calculator, and you should find that you've got a horizontal force of 0,159. Cool. Hope that makes sense to you guys there. How to find the horizontal force. And then I'm going to move on to the next question there. Cool. Kaukela gave us an answer there. Well done. You did really well there. And then someone posted there in the chat. They asked, why didn't you write F nets equal to MA? Because you also, that's also a mark. I'm just wondering for which question you're asking for. If you're asking about, let me quickly try and mark this. If you're asking about this step, why didn't do F nets equal to MA? For this question, you don't get a mark, right? That's why initially I just wrote this because it's assumed that you would understand and know that this is true. But I took the extra steps just to show you guys how it's going to actually work in that case there. Okay, cool. Thank you. Someone made mention that I forgot the SI units there. Yes. Thank you very much. Sorry. Yes, Theo.
Oh, I wanted to make note of Settler's comment there.
Yes, thanks, Settler, for that one. I forgot to put the newtons, the SI units. Please don't forget your units. If it's a vector that they're looking for, please don't forget to put the direction, right? The horizontal force on the ball, and then I can actually just put the direction of that, which is going to be to the right, because they didn't say magnitude, right? They just said what is, calculate the horizontal force. Force is a vector, I must put direction as well there. Then someone just says, can you please try and explain slower? I can't really get you, you're fast. Okay, so again, please note, I'm gonna repeat the steps one by one. What I recommend you do, we do record all of our sessions and we're going to put them on YouTube. If the pacing is a bit fast for you, I recommend you just try stick with us as best as you can, take notes, and then after the session, go back to YouTube where you can replay it as many times as you can, right? So that we don't slow down the rest of the class at that time. And then you can always, again, you're on TikTok. If you guys are keen to get some extra help, you feel like you're struggling with the topic, you can always reach out and try book a lesson with one of our tutors. We got really competitive rates. And then we can help you in that case there. Awesome. Okay, quickly repeating the methodology that I followed for this question for 2.2.1. They wanted us to find the horizontal force on the ball. So what I'm going to do is I'm going to go back and quickly have a look at the second free body diagram we drew, which is going to be, this is the horizontal force, right? It's the X component of our tension. That's the horizontal force. So to find that, I need to find my tension, but I can't get my tension directly. But what I do know is that my tension Y is going to be equal to Fg. So if I can find Fg, I can find my tension Y. So what I did there, I found Fg is equal to mg, did that calculation. Then because I know that tension Y is equal to Fg, I can then equate that in that space. Finally, to find the X component of that, I'm going to use this vector triangle here to go find the tension X. So we can then use our vector triangle. In our vector triangle, we know it's a right angle triangle, right? In this case here, so we can use trigonometry. So then I end up using tan theta is equal to opposite over adjacent. Opposite is my tx, adjacent is my ty. And then simply solving, I just plug in the values I need to plug in and then solve my problem like that. Okay, hope that makes sense for you guys. Let's jump on to the next question. 2.2.2, they want us to find the magnitude of the acceleration of the truck, right? So how do we do that? In this case there, we were just given an acceleration of A. What is the magnitude of the acceleration of the truck? So to be able to do that, we need to try to do a few things in this case here, right? To find acceleration, we're going to simply use Newton's second law. F net is equal to ma, right? And then to be able to do that, we can then just try and find any information that's been given to us. So let's quickly read this one here. There's a group of learners design a device that consists of a light ball on a string hanging from the roof of a cargo truck. This device is used to determine the acceleration of the truck. When the truck is stationary or moving at a constant speed, the ball will hang straight down, but when it's undergoing a constant acceleration, the ball hangs down at an angle of theta, as shown in the diagram. So no super useful information was given there, but we can keep going down and try and figure out the rest of it, right? Then we got the free body diagram that we had to draw, which is okay. And then they said, in this case, the mass of the ball is 50 grams and the angle is 18 degrees. Then they first said, calculate the horizontal force on the ball. So our horizontal force on the ball, we then calculated to be 0.159 newtons. Now we need to find the magnitude of the acceleration of the truck. So anytime we need to do acceleration, we always start with Newton's second law, F net is equal to ma, right? So we can start there, is equal to ma. Now I'm going to ask a question and I want you guys to quickly post this in the chat, right? So posting this in the chat, which object do you guys think we're going to use? Are we going to use the truck or are we going to use the ball inside the truck to solve our acceleration? Because F net equal to ma means we have to pick a specific object. Which object do you think we're going to use? The ball or the truck itself? Alicia just said ball inside the truck. Thank you so much. Another user said the ball. Everyone's saying the ball. Well done, guys. So the ball is great because already what? We've got a horizontal force for the ball, right? And when that ball is sitting there, it's going to be accelerating at the same acceleration as the truck because it's going to be moving as a system together. So once we can figure that out, we can then go find the acceleration of that truck. Cool. So F net's equal to MA. Keeping in mind in this case, we're going to use the details of the ball. So let's quickly plug that in there. What is going to be my F net in this case here? So F net's going to be any force pushing me forward minus any force pulling me back, right? There are no forces pulling me back in this particular case. I've only got forces pulling me forward. So that's going to be then the tension X force pulling me forward, the horizontal force, and then the mass has been given to us, and then the acceleration is something that we are going to do what? Calculate. So let's quickly jump in and do that question there. So our F net we solved is before, same thing as we did previously. That's going to be our Tx, which is mass times acceleration. That tension in the X direction we calculated to be 0,159. The mass of the object or the ball is given to us as it is 50 grams, 0,05. And our acceleration remains a. We need to solve what that acceleration is. And then we can clearly see here that a is going to be 0,159 divided by 0,05. And then when you do that, what is the answer that you guys get there? I'll quickly wait. There, someone gave us a great answer there. Thank you so much. So you should end up with a final answer, 3,1842. You can round it off to 2 decimal places. That's usually what they want us to do. Meters per second squared. And then let's see, they said magnitude of the acceleration. So I don't have to put direction, but I must put the units. Well done to everyone who got this answer correct. We're going to jump on to the next question. All right. Cool. So 2.3, A and B below are two identical blocks, each with a mass of 5 kilograms, joined together by a light, inextensible string. The blocks are being pulled with a force of 65 newtons at an angle of 40 degrees to the horizontal. The two blocks accelerate to the right at an acceleration of 2,17 meters per second squared. So there's lots of information here. Let's quickly go back and highlight the critical information, right? So we know there was mass of 5 kgs. That's going to be useful and important to me. Inextensible string, right, it means the tension is going to be the same throughout the string. So the tension that A feels and the tension that B feels will be exactly the same tension. The blocks are being pulled with a force of 65 newtons at an angle of 40 degrees, useful, to the horizontal. The two blocks accelerate to the right at an acceleration of 2,17 meters per second squared. And the tension in the rope is 26 newtons. Lots and lots of information for us to go and answer this question. Okay, let's have a look at the question. It says calculate the friction on each block. All right, so what I'm going to do there is we're going to start with maybe a block that we've got a lot of information on and move on to the other block. But I think that in this case, we've got lots of information. We can really start anywhere, especially because we know the acceleration and we know the tension. Usually this kind of question is going to be a simultaneous equation question, but in this case, we can do it as is because we don't have a simultaneous equation to solve. It's going to just be two calculations you can do in any order. So I'm going to start with A first, then I'm going to work with B afterwards, right? And then for myself, just to make it useful, I'm going to quickly draw the free body diagram for A and for B. So I know A, I'm going to have a normal force, Fn. I'm going to have Fg going straight down. And then I'm going to have tension pulling me to the right. And then I'm going to have friction pulling me back. And then B is going to be similar, but not exactly the same, where I've got my Fg going down. I've got my F normal going up. I'm going to have two forces going back. One of them is going to be tension. One of them is going to be friction. One force going forward, which is going to be actually at an angle. Let me quickly replace that. And that's going to be the force applied. That's given there. Those two free body diagrams, will help me answer my question. So let's start off with A. A then, we need to then say, again, we need to find the friction. I'm going to use Newton's second law because I'm accelerating. So F net is equal to mass times acceleration. What is my F net? If I assume positive being in the right direction, I always say F net's going to be forces taking me forward minus forces pulling me back. So in this case, what's taking me forward? Tension. What's pulling me back? Friction is equal to mass times acceleration. Now I can substitute my values. Tension is already given to us. That's going to be 26 newtons minus friction is something that we have to solve. The mass of the object is given to us as 5 newtons, and the acceleration was also given to us as 2,17 meters per second squared. Right, now I've got a very simple equation that I can take in there, substitute it, and simply solve for my force of friction. So if you guys want me to write F as the subject of the formula, what you will find is you will then have F is going to be equal to 26, sorry, do this. It'll be 26 minus 5 into 2,17. And then when you solve that, you will get an answer of 12,94 newtons. Right, that's the force of friction experienced by block A, right? It's important. And the question said the friction on each block. So I can't assume that it's going to be the same. So let me calculate the one on block B, right? Separately. Let's quickly have a look at that. So now on block B, I'm going to do the same thing. F net's equal to MA, Newton's second law, M times A. And then we can see here, F net is forces pulling me forward minus forces pulling me back, right? So forces going forward minus forces going back. In that case there, I'm simply going to then go my force applied, but remember it's the X version of that. So I'm going to have my F applied in the X minus tension minus friction, which is equal to the mass of the object times my acceleration. How do we then do that? Let's quickly go in there. So we can easily then find the fact that, okay, the F in the X direction is going to be given as 65 cos 40 degrees, right? 65 cos 40 degrees, and then minus my tension, which is 26, minus my frictional force, which is something that I'm trying to solve, is equal to the mass is going to be 5, and my acceleration is 2,17. Okay, I'll check. Sorry, I see the friction for block A is there. Apologies. I'll double check. I was taking the answer straight from the memo. I'll quickly redo the question myself and double check it with the calculator. Let me finish this solution and then I'll double check it myself. It does happen, guys, where you do find errors in the memo, but I'll double check it and then just quickly check with you guys. All right, and then in this case here, when we try and put everything around, what you'll find is my F, if I take F to the right-hand side and move everything to the left-hand side, I'll have my 65 cos of 40 degrees minus 26 minus 5 into 2,17. And the memo answer for this one, right, for B, is I end up with a frictional force of 12,94, and then I'm going to double check the answer myself, right? In there, let me quickly grab my calculator and then just compare the memo answer to an answer that I would actually get. So quickly, now what I'm going to do is I'm going to double check A first, where again, this step is correct. F net is equal to MA. The next step is going to be tension minus friction, 100%. Tension is 26 minus friction, which is equal to that. Then to get my friction right, I'm going to get the 26 minus that. Let me quickly have a look at this. 26 minus 5 times 2.17. Yeah, you guys are right. It is 15,15. I think there's just an error in this particular memo. And then apologies for that. 15,15 for this question here. 0.15 newtons. Let's also just double check the one for B in case that one's also giving us a problem. So let's double check the steps. Steps again, F net's equal to MA, that's correct. Let's look at the forces. It's FA, but the X component minus tension minus friction is equal to MA. Very important. Then again, the FA, we have 65 newtons given up there and acting at an angle of 40 degrees. So we have 65 cos 40 minus my tension given us 26, also minus the force of friction, which I'm trying to solve for. If I take friction to the right-hand side and bring my MA to the left-hand side, I end up with 65 cos 40 minus 26 minus 5 into 2,17. And then this is 12,94. This one is correct, the 12,94. Cool. Apologies for that, guys. I'll just also double check. Remember, as we do this thing, they do release erratas for certain memos. This is a Gauteng paper. I didn't see an errata, so I'll double check it as we keep going. But thank you very much for pointing it out to me as we keep going. Awesome. I hope that makes sense to you guys. Remember, whenever we're trying to calculate acceleration or anything like that, F net equal to MA is usually going to be your go-to for Newton's laws questions. If the object is not accelerating and it's in equilibrium, then you're dealing with Newton's first law. F net is equal to 0, right? And then you can use that to calculate any unknown force. Awesome. Hope that makes sense. Let's jump to the next question. Cool. So 2.3.2, explain why the frictional forces on the two blocks then differ, right? Okay, so the two blocks will have different frictional forces, even though they have the same mass. Very important. And the blocks, number one, let's quickly go back, are identical, meaning it's the same material, right? And they have the same mass, 5 kg and 5 kg. So why would the frictional forces differ? So remember, even though this is identical objects on an identical surface, why they would differ is because friction depends on the normal force, right? Remember, friction, when you calculate friction, we say force of friction is equal to coefficient of friction, right? Mu S or mu K times the normal force, capital N. Now, if you look at the second object, B, this force here, the 65 Newton force, is going to have a horizontal component, but more importantly, it will have a vertical component. When I have that object B being pulled at an angle, a part of that force is lifting my object off the floor. Now, remember, what is a normal force? A normal force, like I said earlier, is the reaction force to an object resting on a surface. So if I lift that object slightly off the ground, so not that it's off the ground, but I'm making it apply less pressure or less force on the ground, right? In that case there, I've got less of a normal force. With less of a normal force, in that case there, I'm going to end up with less of a frictional force. So if my normal force goes down, my frictional force goes down. How you'd answer this question is in the following steps. So step number one, you would refer to the fact that block B has a force acting upwards, right? That's the first thing, first point to make. Second point to make, it means that block B has a smaller normal force. And then because of this equation here, therefore, block B will have less friction. Okay, 3 marks, those 3 points are how you get your points. So block B has a force acting upwards. That will result in block B having a smaller normal force than block A, right? And because that friction depends on the normal force, block B will have less of a frictional force acting on it. Hope that makes sense to a lot of you guys. Then we can jump on to the next question. If you guys are all together with me, I'm going to pause just if there are any questions before I jump to question 3. Okay, there's a thumbs up there. If you're happy and you have no questions, just give me a thumbs up and then I'll move straight on. Okay, got thumbs up on Zoom there. TikTok, I don't have thumbs up, but I do have, okay, there's a question there. If you put that equation, do you get marks? So the third point, you must either put the equation in, thanks Elisha for your question, either put the equation and refer to it, or simply state that friction depends on the normal force. So if you don't make mention that friction depends on the normal force, you must put the equation. One of the two things is going to then get you the marks for the third mark that's there. Okay. Awesome. Hope that makes sense, guys. Let's jump on to the next question. There's another question before I move on. So can we say that frictional force is directly proportional to the normal force? 100%, right? So as long as you can make mention that frictional force is dependent. So if you say directly proportional, even better, it's a dependency. Or give the equation and make reference to the equation. But once you've shown that because the normal force is less, the frictional force will be less, that's how you get your third mark. Okay. Fantastic, guys. I hope that made this topic a little bit easier for you guys. Let's jump onto the third question. Question 3 is now a question that deals with vertical projectile motion. Okay, and the question goes as follows. It says, a 50-gram ball is dropped from a certain height. The velocity time graph below represents the motion of the ball as it bounces vertically on a concrete floor. The time of contact during the bounce is 0.02 seconds. Ignore all effects of air friction. Okay, before we go too far, I always like to spend some time making sure you guys know how to interpret these graphs. So let me quickly zoom into the graph and let's quickly have a look at what is happening at any given time, right? We were told that a ball is dropped from a certain height. So first thing we can see, this is the point at which the ball is dropped, right? Starts at a velocity of 0. Then we can see in this case, down is positive, because when something is dropped, it's not going to go up, right? Unless you're living in an upside down world, it's going to go straight down when it's dropped. So when I drop the ball, it's going to go down, and then it's going to start increasing in its velocity in the downwards direction, right up until it hits this point here. At this point, the ball hits the ground. Very, very important. Similar to what happened before. And the ball is going to continue being on the ground all the way through until this point here, right? This is still on the ground, hasn't left the ground, right? The reason why it flips sides, remember, the ball starts going vertically downwards, positive direction, hits the ground. So when we start here, ball is, apologies for that, need my pointer, there we go. The ball starts on the ground. It increases its speed as it goes down, speeds up, speeds up, speeds up. At this point, it hits the ground. As it hits the ground, it must change direction from the positive to the negative. So then it hits the ground. This is like, imagine if that ball's like compressing itself into the ground, decompressing itself out of the ground. And at this point, it leaves the ground. Does that make sense? So the top part there, let me name these points. Let's say this is point A. Sorry, let me use a pen. Let's call this point A. Let's call this point B. Let's call this point C, D, and E, all right? So point A, the ball is dropped. Point B, it hits the ground. Point C, it leaves the ground. And then point D is our maximum height. And then point E, it hits the ground for a second time. So I hope that makes sense as I'm unpacking this graph for you guys. And then we're going to be able to answer the questions that follow, right? Someone asked there in the chat, Refuler asks, sir, is downwards taken as positive? Very correct, Refuler. So downwards is taken as positive in this particular question here. And then we can see that up is going to be negative. All right, now let's look at that. We've tried to unpack the graph as much as we can. Let's go answer the questions that follow. So it says 3.1, we need to do what? We need to define a projectile, right? So a projectile is what? It's going to be an object that moves under the effects of gravity and gravity only, right? So any object that is moving under the effects of gravity only, or it's under the influence of gravity only. I'm going to just paste that straight from the memo so we can have a look at it together, so you guys don't have to deal with any more of my terrible handwriting. So define a projectile. it's an object, right, given an initial velocity or not, that when it moves under the influence of gravitational force only. So when you look at the answers as they're given, the underlined parts are really what's going to be very, very important. Someone asked there again, do you have a YouTube channel? Definitely, youtube.com/the learning space ZA. If you're on TikTok, just go to our profile. There's a link straight to our YouTube there. Thanks for asking. All right, 3.2, let's jump on to the next question. 3.2, write down the magnitude of the velocity with which the ball leaves the ground after bouncing. So let's quickly go back. Now, again, we've already given ourselves that beautiful memo, right? So we know that point C, right? Point C being this point right here, is the point at which the object leaves the ground. So we can just go and read off that value, 3,43 meters per second is the speed at which it leaves the ground. If they want velocity, is going to then be in the upwards direction. Okay, thank you so much there, Felicia, for dropping your answer. Magnitude with which the ball leaves the ground is 3.43 meters per second. Let's quickly put that one in there. Okay, then 3.3, draw a labeled free body diagram showing all the forces acting on the ball at 0.77 seconds. So let's go see what happens at 0.77 seconds. So at 0.77 seconds, it's this point here, right? What did we say about point D? The ball reaches maximum height. It changes from moving in the upward direction to moving in the downward direction, right? Okay, when we look at that, again, here's a little cheat sheet. When you do this topic, for 95% of the chances, if they ask you for a free body diagram for any object in free fall, remember by definition, an object in free fall is an object that moves under the influence of gravity only. So your free body diagram will always just look like this. Very important. So for any part of my motion, except when the ball is on the ground, right? So except for between B and C, and except for points E, any other point on any one of these lines, so any point here or any point here, if they ask for the free body diagram, the ball is in free fall, right? What does that mean? It's going to be under the effects of gravity only. Your free body diagram is as simple as that. Your dot, one down arrow, and FG. Easiest 2 marks you've gotten. 1 mark for the arrow pointing downwards, 1 mark for labeling it. As simple as that. Okay, let's jump through to 3.4. Use the information given on the graph and calculate the acceleration on the ball. Okay, so let's quickly go back and look at our graph. Now, when looking at our graph, we need to find the acceleration of this particular ball, right? So there's a number of ways we can do this. So we can either pick out values and use our equations of motion. That's definitely one way of doing it. But I want to show you guys another way to think about this problem, right? Where, especially when dealing with graphs. So remember, when dealing with graphs, so a VT graph, the gradient of a VT graph is going to be the acceleration, right? The area under a VT graph is going to be the displacement at that point. So if we just went and said, well, actually, I can just calculate this area under the graph, I'll get the displacement. Or I want to calculate the gradient, the M at this point there, I'll get the acceleration. The question is asking for acceleration. So I'm simply going to just I can do it in 2 ways, just so that you guys can see both ways. One way, I'm going to just find the area under the gradient of the graph. Another way, I'm going to just do an equation of motion. So let's take between A and B, and I'm going to basically work out the gradient between A and B. We know that point B is 0.04 seconds, right? And the velocity at that point is going to be 3.92. So let's quickly go and do that one in that way. So option A for me there is I'm going to use the gradient. So my acceleration is going to be equal to my gradient, which is equal to change in y over change in x. So change in y, that's my velocity, final minus initial. We saw the velocity at point B, the final velocity, is going to be 3.92 minus my initial velocity. It was dropped, so it's going to be 0, divided by change in x, right? It's the time difference. It was going to be 0 and 0.04. So I'm going to basically then have final minus initial 0.04 minus 0 at the same time there. And then if you put that in your calculator, without even putting it in your calculator, you guys should know what the answer is, right? What is the acceleration of anything that's in free fall? Without doing a calculation, quickly post in the chat. What is the acceleration of anything that's in free fall? Without doing a calculation, quickly post in the chat. Thanks, Alicia, for your answer there. 9.8. Thanks, Tlapanolo, Setla, and Sane. You guys got it right there. So we know we're going to be dealing with 9.8 meters per second. They said calculate the acceleration of the ball, right? So again, acceleration is a vector. So we need to give a direction. It's going to be in the downwards direction. Awesome, guys. That's one way of doing it. The other way of doing it, I can use an equation of motion, right? So I can say from point A to point B, it was dropped. So my initial velocity is 0. Point B, my final velocity is 3,92. The delta T was given to us as 0,04 seconds. And I'm trying to find my acceleration. So let's quickly do that with an equation of motion. We can use VF is equal to VI plus A delta T. Substitute those values in there. VF is 3,92. VI is 0 plus my A. I'm trying to solve. And delta T is going to be 0,04. And then we can see here that A is equal to 3,92 divided by 0,04. Same as before, we'll get 9,8 meters per second squared. Oops, I made that mistake with the previous one. It's per second squared, not per second because it's acceleration. Meters per second squared downwards. Okay. Someone said there, is it not supposed to be 0,4, not 0,04? I can double check for sure. It is 0,4. Thank you for that. It is 0,4, not 0,04. Okay, there we go. I'll just move it closer so it doesn't look weird. Okay, 3.42, the height from which the ball was dropped, right? So to find the height from which the ball was dropped, sorry, there was another question that I just missed out there. Someone said, on their free body diagram, they added tension. Will they still get the 2 marks? Definitely not, right? Because you're going to lose marks for the mistakes that you make. So you won't get your marks. You might get 1 mark for the FG, but you'll definitely get penalized for the tension because that force does not exist there. Okay, let's quickly go down and look at the next question. 3.4.2. 3.4.2, now it says, the height from which the ball was dropped, right? So remember what I said to you guys before? We've got 2 options. I can either, for displacement, I can go find the area under my curve, right? Or I can use an equation of motion, 100%. Okay, so someone says, please do the area formula, 100%, I'll do that. So again, I'm going to work from A to B because A is where it was dropped from and B is where it hits the ground. So the delta Y there is going to exactly be the delta Y of the height of from where it was dropped. Okay, so let's quickly go. The height from which the ball was dropped, I need to find the area under the curve. So my delta Y is going to be equivalent to the area under the curve. The area of a triangle is half base times height. All right. And in that case there, half remains half. The base is going to be my time, right? If you quickly go back, the base is my time, 0,4, not 0,04. I made a mistake in the last one. That's 0,40 times my height. The height of that triangle is going to be the velocity, 3,92. If you can look at that there, let's quickly put that in there. 3,92. And then if you quickly put that in your calculator, you should get half times 0,4 times 3.92. And then you should get an answer of 0,784 meters. Cool. And that's the height at which the ball was dropped in that case there. If you want to do the equation of motion version, we can definitely do that as well, right? So to find delta Y, the equation we can use delta Y is equal to VI delta T plus half A delta T squared. So there we can say our delta y is equal to VI delta t plus half a delta t squared. Let's substitute our values. We're dealing from point A to point B, right? So at point A, it was dropped. I've got no velocity. So it's going to be 0 times our delta t is 0,4 plus half a. My acceleration is 9,8. In this case here, I am going to take, I can just take down as positive, right? So it's fine. So my acceleration is going to be downwards. It's going to be 9,8, and my time is 0,4 squared. And then if you plug that, you should get the exact same answer, 0,784 meters. Hope that makes sense. Manisha asked, what if you use the equations of motion to find the height? You'll get the exact same answer and you will get all your marks, Alicia. So that does work there in that case there. Awesome. Hope that makes sense, guys. To you guys, let's jump on to the next question, 3.5. Okay, then it says 3.5 on a set of axes. Let me just move this question up so I give myself a bit more space. It says on a set of axes, right? Draw a position time graph for the motion of the ball from 0 seconds to 1.2 seconds. Use the ground as 0 reference. Indicate the height from which the ball was dropped and all relevant times on the t-axis of your graph. Now, again, I love displacement time graphs that are for projectile motion because it's literally as easy as tracing out the motion of the object. So let's quickly go back and look at this here. So we know it was dropped from a certain height, hits the ground at B, leaves the ground at C, maximum height at D, and then it hits the ground again at E. So let's quickly draw our axes. Then we'll mark our key milestones. So our key milestones is going to be when it hits the ground at B and it leaves the ground at C. So that's 0,4 and 0,42. Those are 2 points that are important there. And then we get maximum height, 0,77. And then the last one is going to be hits the ground again at 1.12. So it's 1.12, 0,77. It hit the ground at 0,4, left the ground at 0,42. So in this case here, right, I'm going to take downwards as negative, right? And then the 0 point becomes my reference point. So it's literally as simple as where it starts, the object, let me quickly do it in a different color. It's going to start here, and then you're literally going to just have this motion of the ball coming down. When it hits the ground at 0,4, it will leave the ground at 0,42, hit maximum height at 0,77, and then hit the ground again at 0,12. Let me just make that a little bit neater. There we go. And then your maximum height is at 0,77. So that's a nice way of doing the position time graph for a bouncing ball or any projectile motion. It simply looks like the motion of the graph. And if by any chance you chose down as positive, you're just going to have a reflection about the x-axis. I'll draw it on the underside. So you'll basically have a graph that looks like this and that. So the green one, so the orange one is going to be if you took down as positive, the green one is going to be down as negative. As negative. Any other information I can fill in? The maximum height we worked out to be 0,784. So here we'll have 0,784. In the other direction, it was negative 0,784. We've got 0. Don't forget your axes. This is time measured in seconds. And then your y-axis is going to be your position, x, measured in meters. Yeah, and once you've got that, you've basically done your graph as it is. Either do the green or the orange. Don't do both. Very important. Jabu says, I must please re-explain. 100%. So remember, the easiest tip I can give you, the position time graph for projectile motion usually looks like the motion of that object. So my object, right, starts at the top of wherever it was dropped. It's going to move down. It's going to bounce up, maximum height, hit the ground again, because that's what basically happened at that point there. So all you need to do is just map what happens. I move down, highest point, hit the ground, leave the ground, highest point, hit the ground again. You can align that with what our graph was. I was dropped at my maximum height. I went down, hit the ground, left the ground, maximum height, hit the ground again. And that's basically how it'll look on my graph. It'll look like the motion of the object we're dealing with. Awesome, guys. Hope that makes sense. It's 25 to 8. I want to quickly wrap up this question so we can at least try and do question 4 as well in the same lesson. Then at least I know we've covered close to half the paper. Then on Thursday, we're going to finish everything else again. Awesome. If you guys have just joined us, we're doing not projectile motion. We just finished projectile motion. We're finishing it off now. We're doing paper 1 revision, right? We're on question 3, and we're going to go up to question 4 today and finish the paper again on Thursday. 3.6, give one term for the rate of change of momentum. I want you guys to post that in the chat. What is one term for rate of change of momentum? Quickly post that in the chat. There's some quick answers there. Nicole's asking which paper this is. We'll find a place to kind of post it for everyone, guys. Nicole, it's one of the Gauteng province prelims. I'll double check. If it's not last year's paper, it's the year before. Okay. Lots of answers coming in, and this is a very tricky question, right? It's not tricky, but it's deceptive. Someone's asking Thursday what time we're going to be together. Our lives are always 6 p.m. to 8 p.m. up until the end of next week. There's the answer I'm looking for. Kamohelo, well done to you, right? Kamohelo's got the right answer there. Bientle's also got the right answer there. Well done, guys. It's F-net, right? Because impulse is not the rate of change of momentum. Impulse is equivalent to my change in momentum, not rate of change. Rate of change is change in momentum over t. So in this case here, it's going to be F-net, right? Or resultant force. That's the term that they're looking for. We had one of the days in our team, we had a quiz all together, and this question tripped me up. I also said impulse, and actually when you think about it and use your slow brain, you pick up that actually that it's not impulse, but it is F-net. So well done to those that got it. You guys did not get caught out, just like I got caught out last time. Cool. So 3.7, calculate the magnitude of the force exerted by the floor on the ball for the time of contact. And another hint, guys, when you're doing these exams, these questions in between, where they ask you for a definition or ask you to name a term, apologies, those usually give you a hint on what you must do for your next step, right? If they ask you, give the definition of Newton's or state Newton's second law in words, chances are the next question requires you to use Newton's second law. So here when they say, give one term for the rate of change of momentum, and then we know it's F-net, we're probably going to use F-net is equal to the rate of change of momentum to calculate the very next question. So 3.7, calculate the magnitude of the force exerted by the floor on the ball for the time of contact. Okay, so let's quickly do that together. So we know that, let me just move this up to create more space for myself. F-net is equal to MA, but in this case, it's rate of change of momentum, change in P over change in T, right? And how can we break that down? Change in P over change in T is my M delta V over delta T. So I can quickly then work on that basis there. So then my mass for the object was given as, before I get this one, I miswrite it again. Sorry, I went too far. 50 grams for that ball, right? So then that's going to be 0.05 times my change in velocity. So let's look at the change in velocity for this particular thing here. So change in velocity is when I hit the ground and then when I leave the ground. So I hit the ground at 3.94 and I leave the ground at a negative 3.43. So we're going to just go final minus initial, right? So negative 3.43 minus a 3.92. Let's quickly do that. Negative 3.43 minus 3.92 divided by my change in time. I was in contact with the ground for 0.02 seconds. Yes, because it was in contact there. We get this answer here. 0.02 seconds is my contact time with the ground. Can quickly put that in place. 0.02 seconds. Right? And then that's F net. Again, but what is F net? F net, let's look at our free body diagram for when I'm in contact with the ground. So the ball in contact with the ground, because it's got mass, it'll always have Fg. But when it's in contact, resting on a surface, what else will be there? I'll have an F normal, right? So that F normal, my lines aren't going straight today, is going to be the other force. So depending on how you want to do it, you can say up as positive, down as positive. In this case here, we took down as negative and up as positive, right? So down as negative is going to be then Fn minus Fg. So I'll have my Fn, which is my force that the ground exerts on me, minus my Fg. Fg is equal to mg. So that's going to be 0.05 times 9.8. And then I can go and solve for Fn. And you should find that you get an answer of, if I solve for this big thing here in my calculator, what I get is negative 18.375, right? And then on the other side there, I'm going to end up with my Fg. Let me just double check this calculation quickly. Give me 2 seconds while we're busy with this. Cool. So Khaukelo got 18.375 upwards. Well done, Khaukelo. That is the answer for F net. But the question's asking specifically for the force exerted by the floor on the ball for the time of contact. That's very important. Let me just quickly double check my science. I was reading a comment and then got distracted as to where I was. So again, here we've got change in V. So we've got final velocity minus initial velocity. Final velocity is the velocity. We had this negative 3.43 where it leaves the ground. Oh, so actually up is negative. Up is negative, which means I need to just change these signs on the left-hand side. So Fn is going up, so that's negative. Fg is down, which is positive. So then I'm going to have Fn is going to be that big thing, which is 18.375 negative. When I move my Fg to the other side, it also becomes negative, and then that 0.05 times 9.8 will give me 0.49. And then finally, I can put all of that together, and then I get 0.49 with an 18.375, and then you should get a final answer of 18.865. 865 there. And because they asked me for the magnitude, the negative doesn't have any meaning, right? So therefore, Fn is equal to 18.865 newtons. I don't have to put a direction in that case then. I hope that makes sense, guys. So the critical thing with this question is where they try and trick us a little bit is this part is pretty easy to get. What we forget is that F net is not the force that the ground exerts on the object, right? F net is going to be the combination of these two forces here. You're going to have Fg and Fn. right? And because in this question, I had to quickly go up, we chose up as negative and down as positive. I'm going to then say my F net is going to be my force normal plus my FG. And then you can clearly see here, my force normal is negative because we chose up as negative, and my FG, which is mass times gravitational acceleration. I can quickly just put it there. This was M times G, right? And that will then be positive, and then we can solve for Fn, and we get 18.865. I hope that makes sense to everyone. Sarah just joined, asking what grade this is. We're dealing with a grade 12 past paper, Sarah. We're just wrapping up, almost done with vertical motion. We're about to do the last question. Okay, cool. The last question is a pretty chilled one. If a softer ball is used and the time of contact with the floor is increased while the change in momentum remains constant, how will it influence the force on the ball? Right only, increases, decreases, or remains the same? As usual, this is where you guys get to answer the question. If we use a softer ball that increased my contact time, how will the force, right? How will it influence the force that the ball will experience or the ground will experience, right? Only increase, decrease, or remains the same? Quickly post it in the chat. Thank you guys so much for your quick fingers there. Awesome. 10 more seconds. Quickly guess. If you're not sure, just guess. How will it influence the final force? 5, 4, 3, 2, 1. Team TikTok wins over Team Zoom because TikTok gave the most correct answers in that case there. And the answer is decrease, right? Then it says explain your answer. Why will it decrease? Well, it's quite simple, because when we're looking at F net is equal to change in P over change in T, right? If we increase, or let me rather keep it super simple. Sorry, I want to just erase this. To keep it even more simple than that, we know that our delta T is inversely proportional to our F net, meaning an increase in contact time will result in a decrease of our net force. Yeah, Alicia put it there. Impulse is indirectly proportional to the time. And in this case, please note that they're asking about the force. So you must state that the force is inversely proportional to the contact time. But well done for picking that one up. You guys are awesome for this question. All right, if everyone's on board, give me a thumbs up. We've got 12 minutes left. I want to try and squeeze in the last question before we leave. We might take a little bit more time than we need, but I promise you by like 8:05, we'll be done. Okay, thanks, Nicole, for your thumbs up. And thanks again for the guys on Zoom for their thumbs up. Thanks, Alicia, as well. Cool, let's jump into this one here. Question 4, we've got a wooden block slides down a rough 8-meter long inclined plane, AB, right? The initial velocity of the wooden block at A is 2 meters per second. Now, it says, as shown in the diagram below, so we see there, rough inclined plane. Let's quickly pick out the critical information. So 8 meters long, rough tells us that we need to not ignore friction, right? Initial velocity of the box at A is 2 meters per second, as shown in the diagram. And we know that's a 30-degree incline or decline going down over 8 meters. And there's a 2-kilogram mass in this block. 4.1, it says define the term conservative force, right? So when we do that, a conservative force is simply a force for which when work is done, right, that work done is going to be independent of the path taken. That's the simplest way to put it. If you want to get a bit more detail on that, if you go back and watch our recording of work, the work energy and power lesson, I went in a lot more detail about that. So think about friction, right? Friction is not a conservative force. The work done is dependent on the path taken, but gravitational force is a conservative force. The work done there is independent of the path taken. Go watch our recording. It will help explain it in a bit more detail in that case there. Awesome. Let's quickly go into 4.2. Name the conservative force in the above diagram. Quickly post that in the chat, right? In this diagram there, which is the conservative force that we're dealing with that object, the 2-kilogram object? Junior with the quick fingers, thank you for doing that there. The conservative force we're dealing with here is gravity, right? Here's a little quick hint again for your guys' exams. Thanks, Karabo, for your answer. And thanks, Kaukelo, as well, for the correct answer. when dealing with work, energy, and power, doing CAPS grade 12, the only conservative force you guys will deal with is going to be gravity. Another example of a conservative force is like a spring force, but you guys don't really do springs. But gravity is going to be the only conservative force you guys deal with. That's why when you have a system that's only gravity, that's when you use the conservation of mechanical energy. It's a conservative system. Okay, 4.3. State the work energy theorem in words. Quite easy. The net work done on an object, right, is equal to the change in kinetic energy. So think about the equation, right? W net is equal to change in EK. Write that in words, and that'll give you the work energy theorem in words. The net work done on an object by a net force is equal to the change in the object's kinetic energy. Very simple in that case there. Jabu's asking about the normal force. So Jabu, when you think about the normal force, in this case here, very seldomly do normal forces do work, right? Very seldomly do normal forces do work, because generally when an object is moving, it's going to be moving on a surface. So when you're moving on a surface, you're always moving perpendicular to your normal force. And when you move perpendicular, right, fx cos theta, cos of 90 is going to be 0. So remember, when you're looking at the definition of a conservative force, it's a force for which the work done is going to be independent of path taken. And in the case that we deal with, the normal force will never do work. It's always acting perpendicularly to my motion. That's why we don't include normal force as a conservative force. That's why I just said, as a little quick one, the caveat is CAPS grade 12 in South Africa, you're dealing with the conservative force. Only conservative force you're dealing with there is going to be gravitational force. Okay. 4.4, it says the velocity of the block at point B is 6.92 meters per second. Quickly highlight that important information there. Use energy principles only to calculate the frictional force that the block experiences as it moves from point A to point B. Again, remember what I said earlier. If they ask you to define something before, you probably have to use that thing. But in this case, we're going to have a few options, right? We can use the work energy theorem. But for 4.4, I'm going to probably want to use WNC, right? Which is the work done by non-conservative forces. Because when I look at my object, right, if I were to draw a free body diagram of my object between points A and B, I'm going to basically have my FG, right? I'm going to have my force of friction acting up the slope. I'm going to have my normal force acting perpendicular to the slope over there, right? Normal force doesn't do work. Force of gravity does do work, but it's a conservative force. The only non-conservative force I have is friction. So if I do WNC, I'll get like literally directly to the frictional force work, and then I can calculate it almost directly. So WNC, but if you use work energy theorem, you'll still get the same answer, right? Doesn't make a difference. So let's quickly use WNC. It'll be the easiest one for us to be able to work through. So let's quickly put that equation down. We know that WNC, the work done by non-conservative forces, is equal to my change in EK plus my change in EP, right? When we break that down, WNC is going to be equal to my force of friction, delta X cos theta, right? So that's going to be my force of friction times my delta X times cos of theta. Change in EK is simply going to be half M Vf squared minus Vi squared, plus my change in EP will be mg h final minus h initial. Now I can go substitute all the values I've got there. Force of friction, I don't know what that is. I'm trying to solve it. My delta x, so the delta x is going to be this one over here, where my friction is acting, because it's from A to point B, right? It's going to be the 8 meters we're looking at there. I can substitute that there. 8 meters cos theta. What is theta? I'm moving down the incline, but friction is acting opposite, right? It's acting in the opposite direction. So when I'm acting in the opposite direction, so here's my motion, but there's my force. So it's going to be cos 180. Very important. Cos 180 is equal to, again, half. The mass of the object was given to us as 2 kilograms. My final velocity in this question was given to us as 6.92. Remember, I've got to square it. It's a thing minus the initial velocity of the block, I think was given to us as 2. Let's quickly double check. Yes, 2 meters per second minus 2 squared plus my mass again. That's going to be 2 kilograms. Gravity is 9.8. My final height minus initial height. My final height at B is going to be 0. Initial height is going to be this value here, right? So to find that value there, I can just do a little bit of trigonometry. I've got a hypotenuse, I've got an angle theta, and I'm looking for my opposite side, right? Opposite and hypotenuse, I'm dealing with sine, right? So I know that then sine 30 equals opposite over my hypotenuse. If I want my hypotenuse, I can simply just say my opposite is going to be called hypotenuse times sine 30. In this case, my hypotenuse is 8. 8 meters times sine 30 will give me the height. So I'm going to just simply plug that 8 sine 30 in there for my initial height. My final height was 0. Keep that in mind. Final height here was 0 minus my initial height. We said it was 8 sine 30. Cool. Now I've plugged in all of my values. I can then go solve for my final answer there. So let's quickly solve the right-hand side. Quickly plug all of that in your calculator. So you've got half, half times 2 times 6.92 squared minus 2 squared, close bracket, plus, open bracket, 2, close bracket, open bracket, 9.8, close bracket, open bracket, 0 minus 8 sine 30, close bracket. Then the right-hand side, I get 35, comma 6801. And then I'm to solve for my force of friction, I must divide by 8 cos 180. And then you should get 35.6801 divided by 8 cos 180. And I get my frictional force as 4.46. Let me just double check that I did everything correct. And it is negative because I expect my friction to act in the opposite direction, which is great. Let me just double check everything that I did there so that to make sure I did it correctly there. Just to re-put it in, 0.5 times 2 times 6.92 squared minus 2 squared, close bracket, plus 2 times 9.8 times 0 minus 8 sine 30. Oh, sorry. So this, I think I entered this in the calculator a bit incorrectly. This is like 34,5136. And that, it's a negative 34, that divided by 8 cos 180. There we go. That answer looks a bit better. 4,3142. Okay. Yeah, I think the reason why I wanted to double check, guys, is because my answer was negative, but I know that actually I had accounted for that possibility simply because of this, right? Let me quickly do this. Because of this cos 180, that already accounts for the fact that my friction is acting in the opposite direction. So actually my final answer needs to be positive because the negative is going to come from there. So now that I've got a positive answer, I know I'm doing the right thing. Apologies, I just got a call there. Let me quickly go back to my whiteboard. Give me 2 seconds. This is reloading. Sorry, let me just try to reload this. Okay, there we go. It's coming back. Theo, just confirm if you can see my screen on your side.
Nothing as yet, Ernest.
Blank. Okay, let me just try to reload it. Apologies for that, guys. Okay, let me try to reload it now. There we go. Is it back?
Yes.
Okay, cool. Yeah, so 4,3142. And then we need to make sure we've got our SI unit, which is the Newton, for that answer there. Cool. And then wrapping up, like I said, we'll be done by 5 past latest. Okay, sorry. Someone asked there, when do we usually get a negative frictional force, if I may ask? So if you had not put this cos 180, right, you would have ended up with a negative answer for your friction, because then the cos 180 is what basically accounts for the fact that friction is acting in the opposite direction. If you didn't put the cos 180, you would have gotten a negative answer for the frictional force in that case there. But if you account for your signs as you're busy doing your calculation, then your answer should then be positive when it comes out. Cool. Aletta, I hope that makes sense to you there. Okay, 4.5, the coefficient of friction for the last horizontal stretch after point B is 0.35, right? Calculate the distance the block will travel before coming to a complete stop without using equations of motion, right? Very important. So without using equations of motion, which means we're going to be left with using energy principles, right? So we can probably use work energy theorem. So I'm going to basically have my W net is equal to change in EK. And then when we can work that there, W net, the work that's going to be done, when you look at our object there, in the last part, let's quickly go back and look at that. So between B and whatever this final part is, so we're looking at this stretch here, right? No more inclines. I'm just moving straight horizontally, but I do have friction, right? So my free body diagram for that part there will look as follows. I'll keep my dot. I'm going to have FG because it's going to be the force of gravity, and I'm going to have friction, and I'm going to have force normal, right? No force pushing me forward, because what's making me go forward? Simply momentum, right? Momentum makes me go forward. Nothing, no force makes me go forward. All right. Then in that case there, which forces do work? My FG doesn't do work. Why? Because FG in this case here is perpendicular to my motion. Fn, perpendicular to the motion, doesn't do work. But our friction is going to do work, and it's going to do negative work in this case here. Great. So let's plug our values in there. W net is equal to change in EK. W net is going to be the net force. It's going to be my force of friction. All right. So force of friction. Sorry, plug that in. Times delta x times cos theta. Change in EK is going to be my half m Vf squared minus Vi squared. Let's plug our values in. So our friction is going to be mu k times my normal force, right? So mu k times my normal force, I can do that as a side calculation. It's going to be mu k times my normal force. In this case, my normal force will be exactly the same as my Fg. So mu k was given to me as 0.35 times my mass, which is going to be 2 kilograms, times gravity, which is 9.8. If I plug that in there, 0.35 times 2 times 9.8, I get 6.86. It's going to be 6.86. So I can plug that in there. My frictional force is going to be 6.86 times my delta x. We don't know what that is. We're trying to solve for delta x times cos of theta. Again, it's going to be 180 because I'm moving forward, but the friction is acting backwards, 180 degrees away. So cos 180, that's equal to half, my mass is 2. Final velocity, I'm going to come to rest, right? Final velocity will be 0 squared minus my initial velocity is going to be the velocity with which I hit point B. And we were told there that that's 6.92 meters per second. Remember, that's the velocity at this point here, 6.92 meters per second. So I can quickly plug that in there. 6.92 squared. And then I can solve for my delta x. I'm going to quickly solve the right-hand side and then solve the left-hand side. So we're going to have half times 2 times 0 squared minus 6.92 squared. Left-hand side, I get negative 47,8864. And then on the right-hand side, I'm going to divide by that force of friction and cos 180 to just leave my delta x, right? And then that's going to be divided by 6,86 times cos 180. So divide that by 6.86 cos 180. And then you should have a final answer for delta x of 6,98 meters. All right, and they said the calculate the distance. So I don't need to put a direction because it's not displacement. Thanks, Khaukhela, for your answer there. That's a good catch with your quick fingers. And that brings us to the end of today's lesson. Guys, sorry for going over, but it was for a good purpose. I hope you guys found this lesson useful. If you found it useful, please give me a thumbs up, a smile emoji, any emoji that was going to express your emotions at the end of the session. And then I will see you guys again on Thursday for us to finish off this paper. But remember, join us tomorrow, 6 p.m. to 8 p.m. for maths. We're going to finish off maths paper 1, the end of yesterday's session. So very, very important to put everything up there. I see lots of smiley faces on Zoom. I see thumbs up. Thank you guys so much. Hope it was helpful. And you guys must enjoy the rest of your evening a lot. I'll see you guys personally. I'll see you guys on Thursday. But you'll be again with Tsapang and Theo tomorrow to finish off your maths lesson. Guys, have a great rest of your evening. See you guys next time.